Thank you so much for taking the time. I'll try to keep this as short as possible and open up for questions if there are any. I love the name of this conference, and so I'll try to show you a cool machine today. What you see here is a machine that predicts the global economy in real time. Each one of these boxes is a predictive model that automatically adjusts to the changing world, and it's able to predict what happens next. And so I'm just showing you here just as a kind of introduction, but we'll dive a bit deeper into how you go about actually building one of these boxes in a dynamic world. So we will go. I would like to take you on a journey from where we are here and now today in what, in my opinion, is kind of static world and static modeling, to how do we go to technology that allows us to predict the real world or the global economy in real time and build models that automatically adjust to the changing world. Before I start, actually, just to get a sense of who we have in the room, how many of you guys here have built a predictive model? Oh, wow, amazing. Love it. And how many of you have built a predictive model on time series? Okay, cool, nice. So when we talk about dynamic systems, for your imagination, think of them as things that stream in real time. And if you plot that, that's essentially a time series. I just want to kind of get the right mindset. But let's start a bit more formally. We'll come back to this in towards the end. So this is what we will be talking about. A machine that predicts the global economy in real time. We're not going to go, how you go and build the full thing. We'll talk more about how to build, the underlying technology that can help us achieve this. So just kind of as an introduction, I guess, we are a London-based company. We consider ourselves as a deep tech company, and so everyone in our team, has done something pretty cool with technology. A lot of us have PhDs in computer science, physics, chemistry, and stuff like that. And we build essentially the next generation of predictive technology. And the key differentiation to what is out there here and now is this notion of dynamic systems. At present time, it takes a few weeks or few months to build one predictive model. Be that, it doesn't really matter on the type of data, but that's how long it takes. That costs about $50,000 or thereabouts in pounds in terms of human input. And the fundamental problem with the approach is that when the world changes, this model is no longer able to capture the new world. So then we have to go back again and rebuild the model, rediscover the inputs, rediscover the features, rediscover the algorithm, rediscover the parameters. And so our technology is all about trying to have fully autonomous technology that can seamlessly adapt to a changing world. So we're talking about doing things that us humans cannot do. We're talking about unprecedented scale where we have autonomous machines right where the data is. And so we'll talk a bit more about that. So this is the boring bit. I'll skip that. That's just where we come from. But first, I wanna, before we talk about the technology in a bit more detail, I wanna highlight the value of actually predicting the future. So let's take an energy example. If we could predict in real time the demand for electricity, that would lead to cost saving of $400 billion per year just in the US. And so that's that's right there we could, try to save a little bit of the planet at least. If we could predict, in addition to, the 400 billion per year, if we could predict in real time, how many people are going to switch on the hob or the heating, we may decide to burn the optimal amount of fossil fuel. If we could predict how much electricity output will be generated by each solar panel in the world, we can actually, predict how many, tons of fossil fuel we need to burn. There's estimates in food production that about half of the food waste could be actually prevented if we could predict microclimate and demand for food. Microclimate prediction, is doable, but it's it would be hard to build millions of models with the current techniques, where we need to be predicting the microclimate on each field around the globe. Asset management, that's there's similar cost saving there. So that's your pension there. If we had technology that can predict where markets are moving, we could potentially also save your pension. And actually, the total economic value of predicting the future is large. Anywhere you look, there is inefficiencies. When you order your Uber, there's inefficiency. If they could predict how many cars are going to be needed right outside this theater, after we finish this talk, they'll be able to send the right number of vehicles. And you wouldn't have to pay, surcharge for once you go home today, just look around. Everything can be optimized. Anything that in the economy, if we could predict demand and supply in real time more accurately, we can optimize every business on the planet. So that's what we're going to be talking about. How do we actually do that? And so I want to draw your attention to this fact here. There are going to be 50 billion connected devices in the near future. So this is all driven by IoT and 5G. So for the first time in human history, we'll be able to monitor the global economy or the heartbeat of the global economy in real time. That has never been possible before. In all of human history, the amount of data about the global economy put together is going to be dwarfed by the new world coming. Unfortunately, we don't actually have the technology to deal with this new world that is coming towards us. And so it will be pretty cool to be able to have all this data, streaming in real time. And one problem you will observe straight away is that you can't actually put the data of 50 billion streaming devices on the cloud. So one needs to develop technology that will live where the data is. It will be no longer sufficient for things to take 3 days to retrain on the cloud. We have to find technology that will work where the data is, and that means on the device, right at the source. So that's that's super important. So just to give you an example of this, our technology right now is running on a boat cruising in the Mediterranean, predicting wind speed and wind direction in real time. And so that's kind of, if you like, microclimate in a dynamic system. As the boat is moving, it's actually entering kind of different microclimates. So if you had, if you build a model, on the harbor for the microclimate prediction, as soon as the boat sails off, this model will break, and you have to go back to the cloud, to retrain it. But what if you don't have the cloud? What if there's no, connectivity? What if the data is at such a high frequency that you can no longer send it to the cloud and get response in the time you need it? So just wanna, so that's, if you like, we need them to work on devices, and we need them to work in real time, and we're gonna have a lot of data. So those are kind of the problems, and the current technology cannot actually deal with this stuff. So let's talk a little bit about predicting complex and dynamic systems. Why is it hard? Well, it's hard. The first thing that is hard is we have a huge number of unknown causal factors that change in real time. So if something may be important right now, a few seconds later, it ceases to be a causal factor. And so current technology is all about, kind of fixing a model with known inputs and using that to make inferences. But what if, now we live in a world where this is so dynamic that the inputs to the model no longer are static. Current technologies, cannot deal with that. A lot of people talk about data cleaning, but they talk about data cleaning going backwards, and they talk about data cleaning, to look good on the eye. There's, no gaps in the data is aligned, and so on. But very few people talk about, data cleaning in real time going forwards, and cleaning with the intention to optimize the real-world performance of the model. So current technology is all about backwards looking, but to be able to deal with these 50 billion devices streaming in real time, noisy data, we need to have technology that can deal with huge amounts of dirty data in real time. And it's not just to make it look good and for the models to work, but to clean it in an optimal way. And that that requires we'll come to how to do that, but that's something that current technologies cannot do. And then the thing on the right is about scale. Like with the current technology, we cannot build 50 billion models and then retrain them in 5 minutes' time when the world changes. It's too slow, and it's too costly, and it requires human in the loop. Essentially, we don't have autonomous technology to do this. So in summary, we have technology that to build a model is too slow, too expensive, $50,000, to build a model. And the performances are suboptimal for a simple reason, that models only work, essentially backwards. They're not dynamic. So I hinted on some of these things. Just cleaning data with current approaches can take months. And again, people don't think about cleaning data going forwards, but we have to start thinking about cleaning data going forwards. Otherwise, we cannot have these machines perform very well in the real world. And so we, with current technologies, we need a human in the loop. Like, sure, we have AutoML approaches, and maybe the human interaction is minimal, but there's still a human interaction. If we want to, predict the global economy in real time, we need to have fully autonomous, technology that can decide, when it's time to, to reconfigure itself. So that's this notion of adaptability. We need technology that can realize when the world around it has changed, when the processes that generate the data have, fundamentally changed, and we need to have a way, to reconfigure the model. So that's, a lot of criticism for the current technologies, but let's talk a little bit about, the future. Well, I want to pause there if there are any burning, questions on, on the world of today, and why do we need new technology for the, to be able to predict the global economy in real time? Anyone has any comments, questions? Okay, cool. Let's carry on. So at Causalence, we're building what we call the CLPU. The Causalence Predictive Unit. The way to imagine it is it's a box that can self-configure itself. So it's essentially, self-configurable machine learning code, and it's autonomous, fully autonomous, with respect to both the data it's using, how it's manipulating the data, and how it's changing its predictive models. So on the data side, it's able to actually automatically discover valuable data sources fully autonomously. So it's able to actually change its inputs in real time. So if a data stops being causal, it's able to switch it off. And if data starts being causal, it's able to switch it on. It also cleans data in real time. It's able to actually understand what is the best way to clean the data in real time. So imagine you have some variable that was trending historically. It was going up. So, in current technology, people look at that data like, oh, that's trending data. We're just going to apply trend imputation in production and we'll be happy. But what if this variable that used to be trending now starts having mean reverting properties? Then our production system is actually killing the performance of the model because we've essentially hard-coded the cleaning methodology. So the way to solve this is to make this kind of part of the model. So if you can say, our box essentially thinks of data cleaning as just part of the model. So you have a plethora of options how to clean the data, and you need to decide in real time and self-configure yourself to decide what is the optimal way to clean the data right now. And that may change 5 minutes later. And so that's on the data side. So discovering valuable data in real time and also cleaning the data in real time. On the prediction side of things, about being agnostic to technology. Where can this technology run? So we like to push the boundaries of where you can fit this CLPU, and we like to use Raspberry Pi is our favorite little test bed, so we like to put it there, and it's easy to get stuff working on the cloud where you're relying on this humongous infrastructure. It's very hard to get technology running on small devices. The support for real-time processing is actually more challenging than most people think in the sense of building predictive models on the fly, because the engineering is actually really hard. You need to have a lot of there's a lot of software engineering techniques that have to be put in place in order to deal with this inconsistent streaming data. And so people have done it before, for simple things like detecting outliers, but the engineering is super hard when you need to deal with special buffers for the purposes of predictive models. And then the adaptability part is really key. So that's why we call it self-configurable. This unit needs to know when it's making too many mistakes. Needs to realize that the world has changed. Needs to realize that it's time to reconfigure. And it can reconfigure itself in two ways. One is incremental improvement, where it can tune itself inside the box. But maybe the world has changed so much that the box it's time for it to self-destruct, and a new box to come to life. So this is a little bit under the bonnet. So that's what's in the box. So it is 3 parts, if you like. Fundamentally it's a super special optimizer. It's a super special optimizer because it's optimizing, across the full, pipeline of the problem. So it's not just discovering what is the optimal algorithm and the optimal parameters, but it's actually discovering what is the optimal way of cleaning the data, what is the optimal way of extracting features from the data, what is the optimal way of selecting features from the data, what is the optimal algorithm, and what are the optimal parameters, and then what is the optimal way in choosing what is a good model. And so So that's, what we mean by automated machine learning, but it's a totally new approach. Searching this space with current techniques like, random search leads to suboptimal results. And so we have, pioneered a novel way to search through this infinite space, of full model, kind of end-to-end. We call it a full pipeline optimizer. And so we have, we're patenting this, so we cannot talk too much about it, but we have, a teacher machine and we have a student machine, and you can read about it soon when we release the patent. But really, the key here is specialization in dynamic systems. So the machine has been trained to be able to work in the changing world. And dynamic systems, as you know, represent themselves in the form of time series. So, okay, great. I have a few use cases here. So, cool technology, but, how can we go and optimize the world economy? So I just put a couple of hedge funds, a couple of use cases here. We have a hedge fund use case, on-demand transportation, power plants, and transport and logistics. So we can start from transport and logistics. How do you go about predicting cargo volumes between each airport? Imagine you have, whole world, you have all of the airports, and then you have all of the permutations of airports. And actually it gets more complicated than that, because you have different shipping lanes, within the same airport. So the number of models one needs to build to be able to predict air cargo volume delivery between airports in the world, runs in the millions. And then you might, then you're starting to think, oh, how about predicting at different time intervals? What about, 1 day in advance, 1 hour advance, 3 hours, 5 days, 7 days, 2 weeks, 1 month, 6 months. And so if you take all of the permutations of all the shipping lanes and all of the time periods, you end up pretty quickly to a few million models that you need to build. And as we know, it costs $50,000 to build one model, and that model is static. So if you want to do this for real and have a good model, you need to have million models that can adjust automatically without requiring any human intervention. And if you had that, and you can have it now for the first time in history, you're able to actually allocate resources, more effectively. If you can predict the number of, of tons of cargo you need to transport, then you can book the right number of planes, you can book the right number of ground staff, and so on. Power plants, we touched on this early on. To be able to predict, demand for electricity, in a country or a continent, you may need to predict the microclimate in each little region to be able to, if you could predict how cold or warm it's going to become in the next hour, that might help you, predict how many units each household is going to consume. If you, in the future, when we have smart homes, and if you have real-time data of the current consumption, you can build some cool models to predict this. On-demand transportation use case. Imagine you're Uber or Uber competitor, doesn't matter, and you wanna, you want to predict essentially how many cars you will need, or how many passengers are going to travel in each street in each major city around the globe. So if you think about it, if you take each street, it's a separate model, right? And so now you have to build, for each street in each city, you may need to, if you want to get a very accurate model, or maybe even a region, you're still, running into millions of predictive models that you need to build, that all need to be dynamic because, there may be a holiday, the world changes, a new competitor enters, the weather changes. So again, these use cases kind of highlight, or raise the case for fully autonomous, predictive models that change as the world changes. So I don't know if we have time, and I didn't actually prepare a demo, but this is kind of our product and how it works. So for the first time, you're able to just think about the business use case. You're able to think about what I want to predict. You don't have to think about where does the data come from, who do I buy data from, how many data sets I need to evaluate, where, how many data scientists do I need, how much time do I need for them to build infrastructure to be able to build predictive models? How do I know if this, if I bought the right data, hired the right guys, did I wait enough to optimize the models? All these complexities which cost, millions and millions for each kind of problem. What if you didn't have to do any of that? What if you can just come to a place where you just typed in what you cared about, predict. So if you were, in this case, utility company, and you wanted to, to hedge your, the price of natural gas to protect your customers from the prices increasing next quarter, maybe you just go and type, tell me what's going to be the demand for natural gas next month. And then, the technology automatically figures out where to buy data in real time, which day, and it just told you the answer. So that's, that's kind of, the future in our mind. We will have, this ecosystem where we will just be thinking about, optimizing the world as opposed to thinking how to optimize, gradient boosting or, I don't know, ARIMA or whatever else you would like to use. So this is really, where we see the future going. People used to say that software will kind of eat the world, and it did. But now, if software ate the world, we borrowed this quote from the Wall Street Journal. If software ate the world, models will run it. And so that's really, where we believe, the next, big thing in software will come from, is from this notion of autonomous models. So yes, I will go back now to my little map of the global economy, and I will let you guys ask questions they may have. So basically, all the talk was about one of these boxes, but really the power is when you have them in a big network, all talking to each other. So, another way to think about what you're seeing here is a box that can automatically discover a bunch of things that are streaming, and it produces a new streaming thing, which is infinitely more valuable than the things that came into it. And then that valuable thing can now flow as an input to another box, which can take a bunch of other valuable things and make even more valuable thing. And yeah. So that's that. Thank you very much. Very happy to answer any questions that you may have.